All right, one more distribution that is important, especially in statistics, is what's called the chi-square distribution. And I'll just introduce it now, and we'll see it later in the course in certain spots. The chi-square distribution, here's where it comes from. So let's let Z be standard normal and define, okay, and consider the square of that, okay? So if Z is standard normal, then Z squared is gamma 1/2 1/2. Okay. If you're not comfortable with that, then you should look at that for an exercise, because it would be an application of many-to-one transformations. We'd use the change of variables formula, but we would use it in a many-to-one transformation setting. Okay. So Z squared is gamma 1/2 1/2. So now let's suppose Z1 through Zn are IID normal 0, 1. And we define a random variable called SS, which stands for sum of squares, as the sum of the squares of these IID normals. Well, we know that each square is gamma 1/2, and we know that the ZIs are independent, so the ZI squareds are independent, right? So note ZI squared gamma 1/2 for each I, and ZI's independent means that the ZI squareds are also independent. So what does that mean? That means that SS is the sum of the gamma 1/2 random variables, and we know that when we have sums of gammas, we already derived this up above. If we add two independent gammas together, what we get is a gamma where we add up the shape parameters and we keep the same rate parameter. Well, in this case, shape parameters are all 1/2, and the rate is 1/2. So it's gamma with a shape of n/2, right? 1/2 times n, and a rate of 1/2. So SS, so this is a gamma random variable, but it has a special name. It has the chi-square distribution with n degrees of freedom. So n degrees of freedom means that, so where the n comes from, well, n degrees of freedom, it's really with parameter n, but in this case, the parameter is called the degrees of freedom, and n comes from the number of standard normals that we're adding up to get the sum of squares. And we write this as SS chi-squared subscript n for n degrees of freedom. The expectation of SS is the expectation of the sum of ZI squared. Each of the ZIs is gamma half half, right? Well, what is the expectation of a gamma? It's alpha over beta. Well, in this case, since it's gamma n over 2 a half, it's n. Expectation of SS is n. This could easily also be obtained by the fact that we know that the expectation of the second moment of normal 0, 1 is just 1, right? So this is n. So there's a couple of ways to calculate this. This should be directly from the relationship of gamma to the gamma, which we already know. The variance of SS, well, that's a variance. So there's two ways to do this. One is from the gamma, which is alpha over beta squared. Okay. This is from the gamma. Or we could do it from the relationship from the construction of sums squares of standard normals. Okay. But it's a bit easier to deal with it. It's a bit easier to deal with it directly in this case from the gamma, and the density is just the gamma one half density, which we can express in closed form. Well, gamma n over 2 a half, I'm sorry, density. So this is a distribution you'll come across, especially in a statistics course. One of the things to realize here for our purposes is that, as we've seen throughout this chapter where we talked about joint distributions, a lot of the distributions we talked about can be expressed in multiple different ways, and they can be related to other types of distributions. So in this example alone, we have standard normals. We square a standard normal to get a gamma, and we then add those squares together to get another gamma, but that gamma has a special name and it's called the chi-square. We saw up above that when we have gammas and we take the relative size of the gammas, we get a beta. We also saw that if we take uniforms and we take the kth smallest, then that has a beta distribution. The uniform distribution can also be thought of as a beta 1, 1 random variable, and so on and so forth. The inner arrival times of a Poisson process are independent exponentials. The waiting times are sums of independent exponentials, which again is gamma. So there's a lot of different ways. There's sometimes multiple ways to represent random variables, and depending on what type of question you're trying to answer, it's more beneficial in some cases to represent the random variable in a certain way to do the calculation that you're looking to do.